Thank you. Thank you, Maria. So it's a great pleasure to be here. I want to thank all the people also from Xanadu for hosting this wonderful event. And so here I'll talk about the problem indeed of generalization in quantum machine learning using quantum information theory. So the bulk of my presentation is based on a paper that will appear tomorrow on the archive. So make sure to remember to check the archive tomorrow. Okay, so I'll focus mostly, so for me, quantum machine learning will be mostly about quantum classifiers, where the task is to classify either classical or quantum data using a quantum device. And so here you can see a very partial list of papers that also my talk is focused on. And I will always write in my slides some relevant literature whenever I take pictures or other things from some research papers. So the main question of my talk is this. So after training a quantum model using a few known examples, can the model accurately classify even unseen data? And I think this is related also to the last part of Amira's talk. So, of course, one can also empirically check the generalization by studying the testing error, namely see how the trained model performs with unseen data from the so-called testing set. But here, on the other hand, we will take a more formal approach, and I will study generalization using tools from quantum information theory. So we will see using these tools how the Hilbert space dimension, the amount of noise, pooling, all these sort of things can affect the generalization. And then I will also we'll study a sort of bias-variance trade-off for quantum machine learning, and I will link what we found with the information bottleneck principle, again applied to the quantum case. Okay, so the talk is organized basically as follows. So there are three brief introductory sections where I will first quickly describe how to classify classical data using a quantum computer. Then I will describe how and why also to classify some forms of quantum data. And then I will briefly mention how to optimize the quantum model, mostly using gradients. And then I'll finally jump to the main part of this talk, which is the study of generalization. Okay, so let me first define quantum embeddings, like in general. You can also check this Penny Lane website for more information and some very nice examples. So our data here are a collection of pairs like C and X, where X is what we want to classify, for instance, an image, and C is the class. So for instance, here we consider images of animals, and C is the class that describes the animal, like cat, dog, and so forth. So the first thing to do is to load the classical data into a quantum computer. So the first step is to embed the image into a quantum state via a circuit like this one. So this is done indeed by a parametric circuit that in the most general sense is made of different layers of gates, which may or may not depend on X, which is your image, as in this picture here. So after this circuit, the end of this circuit here is what is the state rho of X. So I use the density matrix notation. And so the first part, we embed our data into a state. Then the second part is to process the loaded data to get the class of X. So this decision can be done, for instance, using a P of M, like this, which is the most general measurement that you can do in quantum mechanics. And the outcome C of this P of M is going to be the predicted class of C. So there are other ways of making this decision without the P of M. So for instance, you can measure some observable and then deciding, for instance, the class based on the value of this observable. But these two approaches are quite related to each other. So here I will focus on the P of M as somehow it is a bit more general. And moreover, also via the Naimark dilation theorem, so every P of M can also be efficiently implemented like this. So like a unitary which somehow couples the system to some ancilla sufficiently big ancilla, and then you can perform projective measurements like this on the ancilla to get the class. Okay, so a mathematically related problem, yet physically quite different, is that of quantum state and channel discrimination, which is a very general topic with many applications in quantum information. So here, for instance, I consider the following example. So imagine a self-driving car, which is somehow enhanced with quantum sensors. So quantum light, possibly entangled, somehow is used to screen the outside world. So this light will be partially scattered and reflected by but some photons will go back to the detector camera inside the car. And the state detected by the car, this one here, will depend on the objects living in the physical world. And the task is to make some decision based on those objects. So for instance, stop the car, turn left, turn right, and so forth. Now, this quantum driving car might seem something quite complex for now, but there are easier proposals that actually have been also experimentally tested. So some of these are based on the idea of quantum illumination and quantum radars, where quantum light was shown to provide some advantage for target detection. Another one is the quantum reading of a digital memory, like a CD-ROM. And finally, we have also shown that quantum light can provide advantages for barcode decoding and other physical pattern recognition problems, as we have seen in this recent, as we have shown in this recent series of papers. So here, each physical barcode is somehow read using quantum light, like here, and the different colors in the barcode physically correspond to different quantum channels that scatter light in a different way. So for instance, different wavelengths. So we did show that, for instance, the physical problem of pattern recognition, such as using light to perform handwriting recognition, is maybe algorithmically more complex, but physically simpler from the sensor point of view, because errors here are tolerated. Indeed, for instance, a human eye can instantly recognize that all these pictures here are for a 4, and this is for a 9, even when some pixels are wrongly detected. So we were formally able to show that indeed pattern recognition is easier by showing that the lowest possible training error depends on the fidelity between the two states, this here, that describe either white or black pixels, but to the power of the Hamming distance between images from different classes. So whenever to go from a 4 to a 9, you have to flip many pixels, then somehow, using this idea, we were able to prove that somehow it is simpler, at least theoretically. Then from an algorithmic point of view, what you have to do for making this classification is something like this. So you have to optimize over the detection circuit, optimize over the P of M, and then based on the measurements, for instance, you can also train some some neural network to help you in the classification. So for instance, here we use the convolutional neural networks. Okay, so done with the examples. So how do we actually optimize our quantum model in general? So we use gradient descent. So as you have learned in many other talks, so there are a lot of resources. So for instance, in Penny Lane website is great to learn these parts. And I have also done quite a few works on gradients. So here I will discuss a very biased list of cases where gradient descent can be used for optimization. So as you have seen in many talks, quantum gradients can be computed without any approximation using the parameter shell or the Hadamard test. That can be applied somehow whenever your gate depends on the parameter as in here, which is quite common. But a more general case was discussed. We discussed a more general case in our recent paper, this one here, which came out following a discussion between me and Gavin Crooks during the last year QHack. By the way, I'm wearing the T-shirt from last year because, yeah. But anyway, so our stochastic parameter shift rule applies in the more general case, even when you are taking, for instance, derivatives with respect to any of the parameters inside of your Hamiltonian, like here. And it can also be applied when the Hamiltonian is like describing a many-body system. And then finally, gradients can also be computed exactly for continuous variable distributions and also for the Gaussian boson sampling distribution, as we have as described in these papers here. So last slide about gradients. So another problem that can be solved by a gradient descent is the optimization of quantum programs, where somehow the parameters in your model are not classical, but are rather described by quantum states. And here, since the set of quantum states is convex, gradient descent always converges to the global minimum. And finally, you can also train quantum GANs, so generative adversarial networks using gradients. So a QGAN is like a two-player quantum game. And there are some very nice examples, again, on the Penny Lane website. Here, some demos and tutorial. So our contribution here was to show that training of the QGANs, so when you train the QGANs, the optimization can get stuck into limit cycles when we try to learn mixed states. So for instance, consider this picture here. So this shows the path using gradient descent during the optimization, where somehow the goal was to reach this red point here. So you see that initially the gradient descent goes into the right direction, so it goes like this. But then after a while, it gets stuck and then starts cycling around the solution without ever reaching it. So we have proposed a solution to this issue by adapting the optimistic mirror descent from the classical literature, where somehow the optimism is somehow to guess the other opponent's strategy and fight against it to speed up convergence. Okay, so let's now get back to the main question of the talk here, which is the generalization. So we know how to optimize quantum states and measurements using gradient descent. So the question is, what can we expect? So suppose we have a training set made of T correctly classified images, like this one here from the MNIST. And so we can empirically check the generalization by computing the testing error over the testing set, which is another set of correctly classified images. But even though these images are completely new for the model because it was trained using the training set. So we want to study embeddings. So we want to fix how X, the image, is mapped into a quantum state. And then we optimize over the P of M. And the question that I'm trying to answer now is, what training error or testing error can we expect? Okay, so consider this classic example. And you have seen a plot like this also in Amira's talk. So consider for the moment this classic example here. So we have some data points, so a collection of X and Y, and we want to find the model of this data. So we may consider a very complex model like this, so which perfectly interpolates the data, but this model may have a high variance and overfit the data. So we can also choose a trivial, like constant model, which will have a high bias and normally underfit the data. So the best classical model is then a trade-off, like this one here, right? So mathematically, we may expect a behavior like this as a function of the model complexity or capacity. So here, the capacity or complexity are somehow used in the same way. So the training error, this one here, always decreases as a function of the complexity, while the testing error increases after a while because of overfitting. So the best model is somehow a trade-off. Like there is a sweet spot here, like in the above example. Now, this classic picture has been recently challenged by the success of deep learning, where models with, I don't know, ridiculously high complexity, millions of parameters, tens of millions of parameters, or even more, are able to both have a low training error and a low testing error. So there is the double descent here. So explaining why deep learning works is a subject of intensive research, but somehow one possible idea is that after a while there is a kind of phase transition in the complexity, so after which somehow models with more complexity also show smaller training error. Okay, so now let's get back to the quantum model, and let's first study generalization by defining a loss. So here, for every pair ck and xk in the training set, we first embed the image onto a quantum state via the embedding. Then we will take a P of n, and so the probability to get the outcome C is given by this trace expression. So the single shot linear loss is like the sum of all the probabilities to get the wrong outcome, which is this one here. So ck is the true class of xk. So of course we can also repeat the experiment many times by doing many shots, or we can also do many measurements somehow in parallel using quantum parallelism somehow. And this is fully taken into account by the framework. So I will discuss about this a bit more later. So let's do some math now. So the empirical loss, which is basically the training error, is then the average of the linear loss over all the examples from the training set, which is like this one here. But to study generalization, we also have to introduce something which is a bit more abstract, and that is the abstract classification loss, which is kind of the real classification error. So why is this abstract? So it is abstract because we don't know this probability distribution P, so we just have access to some independent samples in the training and in the testing set. So in our analysis, we choose this linear loss here, mainly because if we fix the embedding, so if we fix this row, then the optimal measurement, so the one minimizing the loss, can be obtained analytically using results from quantum state discrimination, like for instance, Hellstrom measurement. So if we fix the embedding, the optimal measurement to minimize the training error can be analytically computed, and this is what we call here this pi calligraphic T. Where somehow the dependence on T reminds us that this is constructed from the training set. So we can also do the same from the abstract classification error and construct the optimal measurement P star. So this is the true optimal measurement, but we will never be able to find it because we don't know the data distribution, so we don't know this P. And so in this language, somehow the testing error is this one here. So it's written basically like the training error, but you're doing averages over the testing set, as you are using as a classifier, the classifier built by minimizing the training error. Okay, so now let's study generalization as a function of the quantum embeddings. So let's try to write a picture like the one that you have already seen, but for quantum embeddings, also to define the various errors. So you will see this picture many times in my talk to also summarize what I'm kind of talking about. So you may expect that with whatever notion of complexity, the classification error, which is this red curve here, should decrease with more complex models. And the training error basically shows the same trend of this curve here. So on the other hand, the theoretical minimum error that can be achieved by any statistical argument, that is what is called the bias risk. And the difference between this red curve here and the bias risk is the approximation error that here is called A, which depends on the embedding. So if you have an infinite amount of training data, this is basically the error you would get for a particular embedding. And then the average testing error, which is this light blue curve here, is basically the average loss with the classifier. You remember this pi t built from the data, namely from the training set. So it cannot be smaller than the classification error. And the difference between the light blue and this red curve is what I call G here. And G here is the generalization error. So it studies somehow how a data-driven classifier performs with some unseen data. So for models of moderate complexity, we know that the generalization error is expected to increase as the complexity of the model increases. So we won't study what happened here in this regime. This is the deep learning regime, since we cannot somehow reach this regime in the near term, in the near future, I believe. Okay, so now let me jump to the. So in this slide, I summarized the main results of our theoretical analysis that will appear tomorrow on the archive. And I will then explain these results and show some approximations in the, some applications in the next slides. So what we show is that the generalization error is bounded by this B quantity divided by the number of training samples. So it goes to 0 when the number of training samples goes to infinity, as it should be. And then there is like a probability term. So I won't discuss this, but this is like a Rademacher-like generalization bound, for those who know what I'm talking about. While on the other hand, the approximation error can be expressed, depends again on the average encoding states like this one here. So the interesting point is that both these quantities, generalization approximation errors, can be expressed and bounded by entropies, in particular by the mutual information between the quantum embedding and the classical input space. And so here you see the definition of the entropy, and Maria already predicted this. So for those of you, but what is information? So for those of you that never studied information theory, I here write a very quick introduction. So suppose, for instance, that one receives a message with n bits, like this message here, and that the zeros and the 1 occur with probability p and 1 minus p. So the question is that how many bits of information can one extract from this message? So for large n, so a large number of bits, so roughly there are np zeros and n minus 1 minus p ones. So the number of possible messages is given by this binomial coefficient that for large n can be written in this way, where h here is this quantity that depends on p, that is called the Shannon entropy. So somehow this nh can be interpreted as the information, namely the number of bits that one gains after reading the message, or alternatively can also be seen as the amount of uncertainty about the message before reading it. And then the mutual information, which is the quantity that enters in all our bounds, it represents the mutual dependence of two random variables when these are classical, and somehow is the information about one variable through observing the other somehow. And so for classical information, this entropy satisfies many properties. So for instance, the entropy of one variable is smaller than the entropy when you have two variables. So if you read one book, so if you read two books, you gain more information than if you read one book, for instance. So quantum information is defined in a similar way, simply using the von Neumann entropy instead of the Shannon entropy. But quantum information is very different from classical information. And that is because of the quantum entanglement. So for instance, using this Bell state, this quantum state, so the entropy of xy is 0, while the entropy, if you observe x and y alone, is 1. And this is impossible for classical random variables. Okay, so now we know a bit more what is the mutual information and what is entropy. So let's get back to the previous slide. And so here we use entropies calculated with sort of classical quantum state, where Q here represents the embedding, while the C and X represents our somehow classical data. And so you can see how we can bound all these quantities. So there is a lot of theory. let's see what kind of conclusions we can get. Okay, so the first one. So good embeddings should maximize the mutual information EICQ between the class space and the embedding space, and minimize IXQ, which is the information between the input and the embedding. So basically, good embedding should somehow compress the input space, throwing away all the information from X that is unnecessary to predict the class C. And this is similar to how the information bottleneck principle works, as we will see. So let's consider two extreme cases. So in the so-called basis encoding, this one here, different input X, so different images are mapped onto different orthogonal vectors in the Hilbert space. So here, basically, the X and Q are the same. And so for this choice, the approximation error is minimum. So this A is minimum, but the generalization error is maximum. So we are somehow here in this picture. So the basis embedding has two main problems. So first of all, I mean, according to this analysis, it does not generalize well, or in other terms, you need many data to train it. And also it requires a very large space. So for instance, if you consider the MNIST database, so here each image has like 28 times 28 pixels. So if each pixel has like 8-bit color, then roughly we need 6,000 qubits, which are quite a lot, right? So this is one extreme case. The other extreme case is the trivial constant embedding, which has, of course, no information about C and Q. And so this trivial choice has the maximum approximation error, namely, basically, you have a 50% chance of getting the wrong outcome, but the minimum generalization error. So we are sort of here in this picture. Okay, so another interesting result is that bigger Hilbert spaces also have lower approximation error, but larger generalization error. So for instance, we have performed a very simple numerical experiment using two different classes, so C0 and C1, distributed via according to some Gaussian distributions. So we use a simple embedding, which is called angle encoding, which is this one here, that we also took from Maria's review. So here you have also to normalize the data X. But we also extend this simple embedding by taking copies, so by extending using n qubits. So what we have shown is that the approximation error using this embedding decreases with n, and while the generalization error linearly increases with n. So here the 1, 2, 3, and so forth is this n here, so the number of qubits. So this is not just, so this is of course a numerical result, but somehow this thing here is, on the other hand, an analytic result, where we have shown somehow that the approximation error decreases exponentially with n by some fidelity quantity. And this is based on some asymptotics that I won't discuss here. Okay, so another interesting conclusion, maybe a bit intuitive as well, is that low-dimensional embeddings and low-entropy data sets generalize well. This is kind of obvious somehow. But to be also precise for generalization, so we should keep the embedding space small, but the embedding Hilbert space doesn't necessarily have to be really small. So the important point is that rho of X, so our embedding, should scramble somehow the information in a small subspace of the full Hilbert space. And so this is kind of intuitive, and it was indeed already discussed, for instance, in this paper by Seth, Maria, and others. So in our analysis, somehow we quantified this a bit using, again, fidelities between quantum states. So the idea here is that a good embedding should cluster the data from the same class into nearby points of the Hilbert space, like here. and separate as much as possible different points from different classes, as in this picture here, where you have, let's say, 3 classes, red, green, and yellow. However, due to the trade-off between the approximation and generalization, this ideal picture cannot be really achieved. And so, okay, so another interesting fact is that, so to favor generalization, somehow the final Hilbert space should be kind of small, but the initial Hilbert space can be big. So what we can do is that we may iteratively discard information via pooling layers that, I mean, for instance, so this is a picture from this paper here, where they have introduced quantum convolutional neural networks, which indeed have this pooling layer where somehow you throw away some qubits. So one can show that, so we show that pooling favors generalization but harms the accuracy. And you can also show this formally using data processing inequality. So if it is possible to achieve low training error with pooling layers, then use them, because generalization here can only be better. Okay, so this is my last technical slide. So I want to show how also our results are somehow linked to the information bottleneck principle. So if we treat the embedding Q as a sort of hidden layer, then the information bottleneck principle says that we should optimize Q to minimize this information bottleneck. It's called the information bottleneck Lagrangian for some values of beta. So here beta represents, so here beta allows us to explore the trade-off between approximation and generalization. So we found that the solution to this information bottleneck, so the minimum of this information bottleneck Lagrangian can be written as a kind of self-consistent vector equation that can be solved via iteration. And from our numerical experiment, we see that embeddings constructed by solving the above equation for low beta, like here, this is for low beta, as you can see, normally have a very large risk, close to the trivial 50%, but small generalization error, while for large beta, the embedding shows low average loss, close to the theoretical minimum value given by the bias risk, but larger generalization error. So we can also see this geometrically on the block sphere. So for instance, for moderate values of beta, like this 1.5, you see that the embedding starts to cluster data close to each other, like here, but without separating the different classes. So you see that, which are here represented by either red or yellow points. On the other hand, for large values of beta, somehow the data are clustered and well separated, although there are still points in the wrong cluster. So for instance, here you see some yellow points, and here there are some other reds. And this error cannot be completely removed, as the bias risk also here is non-zero. Okay, so this is my conclusion. So we have introduced quantities from quantum information theory to study the generalization in quantum machine learning. So in particular, we focus on how to define a good quantum embeddings. So we have studied then how the Hilbert space dimension, pooling layers, but also the amount of noise, even though this I haven't discussed in this talk. So how all of these things affect the approximation and generalization capabilities of quantum models. And there are many open questions, of course. The main one, which is more for the long term, I think it was also appeared also in Amira's talk, is to understand what happens with models of extremely high complexity, like in the deep learning, to see whether there is a sort of deep learning transition after which also models, more complexity is also good for generalization. And another open question is this with the study of different cost functions. So I personally don't expect our results to be too much affected by the choice of the cost function, as we basically get the same results via information bottleneck principle, which is kind of cost function independent. But this is, of course, a very interesting question, and that is worth exploring more formally. So with this, I'm finishing. So I thank you all very much for your attention.
Great, thanks, Leonardo. Thanks very much.
Thanks, Maria.
So, you know that I absolutely love about this perspective, that it's basically merging theory that we actually have about quantum computing through quantum information theory, which is like a long tradition that has discovered a lot to understand machine learning. And in my own research, I realized over and over again how similar they are. So some of you might have heard of quantum state discrimination, or combine, sorry, to compare quantum distributions like quantum states, which is like traditionally things that you do in quantum information processing. And in machine learning, this would be like related to GANs, to classification problems. And so there's, I think, a lot to do. However, so obviously quantum information processing uses also very deep quantum language, and I assume that lots of our viewers, or some of our viewers, might not really know what's a trace even, or they got like really confused when it came to, well, the entropy part. I think you explained really nice. But so can I ask you, for those who are more the hacking and the doers and the people who maybe start getting into these steps, could you formulate in 1 or 2 sentences, what can they take out of your results? So if they are tomorrow trying to pick an embedding or something, what should they look out for? I know this is really the hardest question you can ask a researcher, like say something about practically, but maybe you can make a couple of statements just as a summary.
Right. I think what I personally think, so if I want to write like some numerical code right now, also to check generalization, so I haven't done that yet, but I would personally start studying this pooling idea a bit more. So because this pooling idea is really this idea of discarding information, but is also learning to discard information which is irrelevant to predict the class. So of course, I don't know how to do that. I mean, it makes perfect sense to me, but again, also trying to quantify this a bit more, I think this would be a very interesting topic. And so other conclusions is that, of course, one can study this bounds also to check, for instance, more formally how to define good embeddings, and somehow this is what our prediction, at least, so our prediction of what you can expect. So for instance, if you increase the Hilbert space, you might observe like a smaller training error, maybe larger testing error, and so forth. So this, I think, is like a summary of what are the kind of predictions of our theory.
Great, and if I might also add, maybe as an intuition, those pictures you showed are very nice, that a good embedding just embeds data of different classes far apart from each other so that we can make easier decisions, right? I guess this is an intuition that also, like, people, I don't know,
it's also your data. It's not really...
Well, it wasn't my intuition, though. That was Seth's whole idea. But yes, great. Thanks a lot.
But you see also here that this is the ideal picture. You see that, for instance, that is more like a real world case. You see that there are still wrong. So even when the data are really well separated, you see that there are still data into some wrong class, right?
Great.
So in general, I think you cannot really achieve this perfect case in general.
Yes, I mean, I guess once you have your data separated somewhere, machine learning gets easy. So that's actually a good take-home message as well. Two a bit more specific questions. We have one about, and I don't know who asked it and why, but we have one about VC dimensions. So what you basically talk about, when you talk about generalization, you used a method to compute a bound on the generalization error that's based on the Rademacher complexity. Mm-hmm. Now, a VC dimension is just a similar or different method. I think Amira mentioned it. Could you do the same computation with these tools?
Well, actually, I've always had similar ideas in my mind for quite some time. And I know that the VC dimension is is used a lot in theoretical machine learning. And I always had this idea of trying to understand this VC dimension and calculate for the quantum case. But I've always found the VC dimension quite hard for me to understand. Maybe because it's a concept which is quite different from my background, which is more like quantum physics and these sort of things. So when I learned about the Rademacher complexity, I started already doing calculations because that was something that was easier for me to process. By also doing this Rademacher complexity argument, so I also learned a bit about the VC dimension, but the way I learned the VC dimension is again starting from the Rademacher complexity and then somehow doing some calculations from this quantity. So I think one can do that. The point is that I don't know how. So I'm not able to do that, but it's definitely something interesting for me.
Maybe I link you up with someone like after the talk. Actually, this leads me to a question I wanted to ask you anyways, out of personal interest as well. Since you always describe yourself to me in some sense as like being someone who comes to quantum machine learning as an interested person from the outside, who actually has a different research field and now tries to find how this is mergeable. So what was your experience in this manner? Is there anything in quantum machine learning that totally confused you? Like, when you started reading papers and you just didn't really understand like what they were talking about, or was it just you started reading papers and they were all, oh, this is a language I understand immediately? Is this something like that?
Good question, actually. So coming also, let's say, from some, I don't know, more theoretical or formal parts of quantum theory, I've always been interested a lot in, let's say, understanding of machine learning. So why machine learning works, why deep learning works. And I've always tried to read that literature, and I always found it quite hard for me to understand. So that was something a bit confusing at the beginning, and also something which is quite confusing for me is that there are tons of algorithms, so tons of possibilities to do machine learning, random forests, neural networks, support vector machines, and I didn't know somehow which one to read, right? Because there are so many things, they seem to be quite different from each other, and so different algorithms, and so I was a bit scared by this, by all of these things. Right. So somehow also one reason why I think the information theory point of view is nice is because somehow it's does not depend on the algorithm. So it allows us to make some predictions without fixing an algorithm and doing somehow calculations. So of course it's based on other things like entropy, information, but somehow does not depend on the algorithm. And this is what I like about the information theory part, but I also can see that might be a criticism to this sort of language.
Yeah, well, definitely not for me, but maybe if you actually describe something that I very much experienced myself, because when I started with machine learning, I opened textbooks of machine learning, and what I was introduced into was the practical side, what are neural networks, how they train. So it was almost manuals that you read. And in the first couple of years of doing quantum machine learning, I always thought that was what machine learning is about. And then I started realizing after many years that there is machine learning theory. And if any one of you out there wonders about the same thing, so the theory of machine learning that is model independent to a certain extent, that doesn't really care about benchmarks. That's, for example, called statistical learning theory. That's the traditional theory. And it's at the moment moved into the modern regime of like deep learning. So at the moment, a big question is, as you heard on this double descent curve, what happens if we take statistical learning theory and move it? So yeah, so I agree with you very much that where's the theory in machine learning that takes sometimes years to find out. And once you find it as a physicist, you're so happy because it's actually extremely beautiful. Yeah.
Yeah, I completely agree with that.
Cool. Let me ask you one question about, because I have you here as one of the, I'm actually trying to think, but I think you're one of the few representatives in this QHack edition that is completely in academia, and that also decided from having opportunities in industry, like to go into academia. So I just wanted to ask you a bit about your perspective. Why did you do it? What you miss from, like, you know, your former employments, and what's actually the beauty of working with students, working with big institutions and admin, you know, and just like being in that sphere of research.
For instance, I love the academic position, to be honest. So I like a lot having to deal with students. So I like also the teaching part. So of course it takes some time. So I cannot spend all of my time doing pure research as I used to do when I was like a postdoc or like this. But for me, I mean, I really like the teaching part. Maybe a bit less the exams, but the teaching is great. And so doing quantum information in the academia, so you have the beauty of the academic environment. So you have students that are interested in the topic, so you will see how to train these students, and also you will see them getting better through time, which is always a good experience for me. And then of course, I mean, so there are so in terms of the research, so still we have a fair amount of time to do this sort of things. So for me, is the perfect environment, so to say. So what I miss from the let's say industry point of view, that's a good question. Let me think about that. So there are so also the social part was nice, and also, yeah, I don't know, maybe the free time. I don't have much free time now.
That is the strangest thing I've ever heard, that you have more free, well, I guess scientists always have a problem with being workaholics. And okay, so I know that also part of your answer was directed against me, because I sent you a couple of questions I might want to ask beforehand, and one of my questions was like, what's annoying about students? So I realized that right now you said like, I love the students, so you don't have to answer the question, what's annoying about your students? So obviously I don't mean this for sure.
No, I mean, of course you can be lucky, or so sometimes also students can, it really depends, but it really depends on the student, but in general my experience has been good.
That's beautiful to hear. And how was it actually to go back to the institution where you got where you kind of did your education with? Because so I remember 2 years ago I gave a talk at the university where I did a master's degree, and it was very strange to come back and all of a sudden you're on the other side of things and you wish people would have told you things before, and was that like emotional, or was it just like, okay, I fit in here as usual?
There is always this emotional thing, because for instance, when I left somehow my hometown, and I mean, I first moved to Turin and then to London for quite a few years. So I remember the first time abroad, so I was always missing something of my hometown. But then after a while, you start, I don't know, you're starting to like also the new environment. And after many years, or at least that's what happened to me the first time, when you move back, you miss the things from the other place, right? So that's at the beginning. But then also you realize, I mean, you are surrounded by wonderful people. Basically all of them. You can also go out again with your friends from childhood, and so at the end everything is great.
Okay, in the end everything is great. Nice. I get pinged here to ask questions about gaming. So I know that when we talk about scientists, we always have to ask them if they do gaming. I'm not sure why they're coming up so long. Let me phrase it in a different way. one question I always had and forever had, and this is also to the admin who's in the background who you haven't seen, Tim, who's part of the Xanadu team. Why do you buy a different type of chair if you're a gamer than normal people? Because we cannot really claim that there's only one type of chair that's comfortable. So my first question is, do you love computer games? My second one would be, why do you have to buy a different chair if you're a computer game lover?
Well, the first question is easy. The second question, I don't know. I mean, so the first question, yes, I love gaming. I used to, actually, I'm a big fan of anything about Mario and Zelda games. But I also play.
We're not talking about Super Mario, no?
Yes, I am.
Really? Does that still exist? The one with the mushrooms that jumps up?
Exactly.
Yeah. Okay. Cool.
I love that sort of things more than, let's say, the game for let's say more mature people. That, I mean, I also prefer these easy games. That's what I like the most. But I also play some other sort of video games, of course. And for the chair, I don't know, to be honest, about the chair. So for instance, I also have like a sort of gaming chair, but I play most of my games in the sofa. So I use this chair for work.
Okay, I see. So it's all just a
this is my working chair. It's not my gaming chair.
Okay, cool. I'll ask Tim afterwards. Oh gosh, there's a question if Mario can be played through by a QML. So basically, can we have, oh gosh, this is obviously a question that I don't know if you know the answer to. But
well, this question no, what was that? The Atari games. So I don't know if there is a quantum version of the Atari. So you know that this reinforcement learning, so classical reinforcement learning paper for playing video games. Maybe there is also a quantum version, but I don't know.
Yes, I mean, the interesting part of this question is obviously, as many of you know, in classical computing, back in the day, people thought, what do we use computers for? The answer was, maybe scientific computations, we can build atomic bombs or whatever. And then, I mean, it's the same stage where we are now. Do we do quantum chemistry with them or what? And then in the end, obviously, gaming came and changed the market entirely. So maybe this is not such a stupid idea. We just need something that's addictive and that's quantum and needs to be quantum. And then we researched for 30 years for quantum advantages, and in the end, it's just quantum fun that makes all the difference. But I don't even want to know. Okay, great. Let me just ask you one last, a bit more personal question. I heard that you are expecting a child, so you're becoming a father.
Not me.
Oh, sorry.
My partner, of course. Yes. So I'm super excited and a bit scared as well.
Yes. My question would actually be: does that change the way that you work? And I'm asking because I sometimes speak to mothers who are professors, and they often tell me that the moment they had children, they stopped being so worried about everything, and they were just working basically to feed their children, and it was a lot more put into relative points. Most of you guys out there who are PhD students and masters think that this is the only thing in the life that's important and is very stressful. So does like becoming a father put everything into perspective all of a sudden, or it's no magic?
I don't know, because I'm not a father yet, but I agree with this point of view. So for instance, when I was like a postdoc, but my main goal was somehow to find some more stable position. But I agree that somehow, I mean, there are also more important parts in life, and I think being a father is, of course, something. I'm a bit scared, to be honest, but I'm also super excited. So, and definitely that's my what makes me I don't know, what takes most of my thinking time right now.
Great, that's how it should be. Okay, Leonardo, thanks very much. We are back with QHack 2021 in a few minutes, and we will also have a look at the leaderboard in a couple of minutes when we're back and see how you guys are doing out there.